Now we are going to look into a structure theorem about two connected graphs. And it's called an ear decomposition. So given a graph G, an ear is a path we add on to G that has the property that the endpoints of the path were in G. Now an ear decomposition is a sequence P0 through Pk with the property that P sub 0 is a cycle and P sub I is an ear of the union of the previous parts in the decomposition. So in other words, an ear decomposition looks like you start with a cycle and then you start adding on ears. And so what makes this kind of weird is that, the ears don't have to just meet the cycle, they can meet any previous ear in the decomposition, possibly different ears. And of course, I didn't have this example, but you could also have them meet endpoints from previous ears. To point out the one special case, if you start with a cycle and you tried to add a path where both the endpoints were the same, that would not count as an ear. This should be viewed as a generalization of a result about connected graphs. So one of the results about connected graphs is that you can put the vertices in a sequence with the property that the induced subgraph on the first I vertices is always connected. So in this case, instead of vertices, we're looking at ears. All right, our main theorem is that G is two connected if and only if G has an ear decomposition. To prove the reverse direction, we first need to show the following lemma. If G is a graph and P is an ear and G minus P is two connected, then so is G. In particular, to show it's two connected, what I have to show is that given any two vertices U and W, there is a path from U to W in G minus V for any V. So we're going to take three vertices in the graph. If U and W are in G minus P, then we already know there must be a UW path in G minus V minus P. If V is on the path, that's because G minus P is connected. If V was not on the path P, then this is because G minus P is two connected. And so deleting the vertex V still gives you a connected graph. All right, so now we know at least one of the vertices U or W has to be on the path. Without loss of generality, let's assume it is U. And there are two different directions you can go on the path. Particularly, there are two different ways. There's a way to get from U to V0, and there's a way to get from U to VK, which are the ends of the path. Since G minus P is two connected, you should be able to find a path P1 from V0 to W and a path P2 from VK to W. In particular, you get at least two different paths from U to W. And at most one of them can contain the vertex V. So in particular, there must be a path from U to W in G minus V. And therefore, no vertex V can be a cut vertex. And thus, the graph must be two connected. All right, so now we get into the proof of the theorem. First, we're going to suppose we have an ear decomposition. Then we know P0 is two connected because it's a cycle. So then we could apply induction on the number of ears. And so in the inductive hypothesis, we're already assuming P0 union P1 up to Pi is two connected. Then by the previous lemma, if you look at P0 through Pi plus 1, you remove Pi plus 1, the result is two connected. And so by the lemma, the union once you add Pi is also two connected. And thus, G must be two connected. In other words, when you keep gluing ears onto a two-connected graph, the result is two connected. Okay, now let's do the other direction. Suppose G is two connected, and we're going to let H be the largest subgraph that has an ear decomposition. We're going to claim that H is, in fact, the original graph G. If not, there must be two vertices that share an edge that is not an edge of H. The reason why we know that is because if V of H is already V of G, then every vertex is in our subgraph, but if it's not all of G, there must be an edge missing. Conversely, if there are vertices in G that are not in H, then because G is connected, you should be able to find a path from that vertex, say X, to any vertex in H. And then going along that path, you're guaranteed to find this edge at some point. All right, so if X and Y were already vertices in H, then X, Y, that edge, is in fact an ear. And so H plus E has an ear decomposition, which contradicts the choice of H being the largest subgraph with an ear decomposition. So then we are in the second case. We want to show H is equal to G, and currently we are looking at a pair of adjacent vertices where the edge is not in H. We've ruled out the case where both endpoints are in H, so we can assume X is not. If Y is also not a vertex in H, then you can try to find a path from X, Y to H. And then going along that path, we can eventually arrive at an edge where X is not in H, but Y is. So we can assume we're in a situation where we have found an edge where one endpoint is in H and the other is not. So now we're in that situation. Since G is two connected, deleting one edge is not going to give you a disconnected graph. And so we know there has to be a path from X to Y in G minus that edge. And particularly once you add that edge back in, we know that G has a cycle that contains the edge XY. And since we now have a cycle, C, and since Y is not a cut vertex because G is two connected, we know C has to contain at least two vertices from the subgraph H. In particular, so we've got this cycle C, and we know there's at least two vertices from H. Well then, going along this path, we're going to get out of H for a little bit, and then the first time we get back into H, we now found an ear that we could add to H, contradicting the choice of H again. And thus we see that if you take the maximum subgraph created using an ear decomposition, it must be all of G. So this proof takes a little bit of work. Part of the reason why this proof is a little bit convoluted is because a graph can have more than one ear decomposition. So this proof does not proceed by giving a specific ear decomposition and then proving that it hits every edge. It's worth pointing out that there's a similar theorem for two edge connected graphs. Instead, you change the word ear decomposition for closed ear decomposition. And then the main change is that now you have to allow closed ears, or ordinary ears like we had before. So what is a closed ear? It's similar to an ear, just now you've taken your graph G, and now you've added a cycle C that has the property that it has one vertex V that has at least two neighbors in G. So it's like you took an ear and then you collapsed the two endpoints together. But because of how ears work, that means that you have to have degree 2. So in particular, this situation is not allowed. No, wait, I mean with the path, right? Because this would no longer be a closed ear because this one vertex has degree 1 to the rest of the graph, corresponding to the fact that there's a bridge here. All right, so now we're going to finish by discussing the block graph. So when G is not a connected graph, you know that G is a disjoint union of its connected components, and then each connected component can be given a spanning tree. So this is going to be a similar construction for understanding two connected graphs. The idea is that suppose G is connected, then it turns out there's a way to somehow decompose it into two connected subgraphs in an understandable way. And then each two connected subgraph could be understood using convex ear decompositions. So a subgraph of G, induced subgraph of G, is called a block if it is a cut edge or if it's maximally two connected. So if you talk about maximally connected subgraphs, those turn out to be components of a graph, and it's clear that the components are disjoint. It turns out for us, blocks might not be disjoint. You could have two blocks sharing a cut vertex, so the structure is a bit different. And so here's what we do. To understand the structure of the blocks of a graph, we create a bipartite graph called the block graph. So one side of the bipartition consists of these cut vertices, the vertices that pop up on the intersections of blocks. And then the other set represents the blocks themselves. And then we're going to have an edge in our bipartite graph from x to b if and only if x is in b. And so this block graph is supposed to help us understand how the different blocks are related to each other. So for instance, let's take this graph. We see it is connected. We see that there are these maximally blocks. The triangles here are blocks because they are in fact two connected, being cycles. And then you see that if you add any other vertex beyond it, there's a cut vertex. And so we see there are these 5 blocks. I'm going to label them, or 6 blocks. I'm going to label them in order B1, B2, B3, B4, B5, and B6. And then we see there are these cut vertices, W, X, Y, and Z. And so on one side I have W, X, Y, and Z, and on the other side I have the blocks. And so then I've indicated the edge relationships. So the point is, given the block graph, you know how the blocks are related. Then to completely describe the rest of the graph, you just have to describe the blocks. And you can do that using a convex ear decomposition, possibly. In this case, it's not necessary. One thing you might notice is that the block graph does not have any cycles, and so that is a homework exercise to show that the block graph is always in fact a tree. And a stronger exercise we won't do here is that if you had block graphs of 2 different graphs that were isomorphic in a way that, preserves the bipartitions and each of the corresponding blocks, and one side were isomorphic to the corresponding block on the other side, then you actually have the same graph up to isomorphism. Unless if you know the block graph and you know the structures of the blocks themselves, then you actually know the graph.